This video is part of the Commercial Building Electrical Design series. It's part of the introduction, and we want to do just a quick basic electrical theory review. Don't want to get too technical here, but do want to cover just a few concepts and define a few terms and units that will help us as we move forward. So first we're going to talk about units of measure and how they're defined. And so when we talk about electrical systems, sometimes it's hard to visualize this. So oftentimes it'll be compared to a water system that has a pump and a valve or something that can inhibit the water. And so when we look at this, we see flowing through this system is water. So this is comparable in an electrical system to the flow of electrons, which we call current. So the water is comparable to current. And we currently measure this in amperes, or abbreviated as amps, and then you may see it abbreviated mathematically as the capital letter I. So anytime you see I, that's amps or current, and this is what flows through the wires in our circuits. Second, we need something to actually push the water through the system, or cause the pressure, and so this is usually done by a pump in a water system. This is comparable to a voltage source in our circuit, and so this creates what we call the electrical pressure, which causes the electrons to want to flow through the circuit. And so pressure then is comparable to voltage, and we measure this in volts, which mathematically is expressed as the capital letter V. So finally, in this system, we can have, while we have free-flowing pipe, we might have instances where either the pipe narrows or we have a valve or something that might inhibit the flow of the water. This is comparable in an electrical circuit to for simple terms, a resistor. So here we would say a valve would be comparable to resistance or impedance, we sometimes call it, and we measure this in ohms. And so we can see this represented a couple of different ways in mathematical equations. It can be an R when it's resistance, or omega is for ohms, or sometimes you'll see a Z used when it's a more complicated impedance, which involves resistance and other factors like capacitance or inductance. So we want to talk about how these units are related in a basic circuit, and so to do that we will draw on Ohm's law, which is one of the first and basic mathematical equations or relationships in electrical circuit analysis. So Ohm's law tells us that the voltage around a loop in the circuit has got to be equal to the current flowing in the circuit times the resistance in the circuit. Of course, this is an incredibly simplified circuit here, or a very simple circuit. We can have multiple resistors, we can actually also have multiple current paths and multiple voltage sources. But the point is, once we quantify those, we can go around any loop and add them up, and it should maintain this relationship. And of course, mathematically, Ohm's law can be expressed as V equals IR, which is voltage equals current times the resistance, or it could be impedance. So as we talked about, you can have multiple loads or multiple resistors, and so there's a couple of different ways those can be configured. So the first is if the loads are in series. So here you see we have our voltage source and we tie our loads input to output, and so that puts them in series with each other. So a couple of observations we can make here. When the loads are in series, the current through each load is the same. So you see here, as the current flows around, there's no other way for it to go, so it has to go through each load. So whatever current flows through here as well. And so we can express that mathematically just to say that the total current is equal to the current through I1. It's also equal to the current through V2, and the current through V3. Now the voltages across each of the loads, that can vary. So depending on the resistance, if all the resistances are equal, then you should get the same voltage drop. But if there's any difference in them at all, you're going to have a different voltage drop across each one. What we do know, though, is if we add up the voltage drops, V1 plus V2 plus V3, that they should equal to the total voltage of our source. So current's the same all the way through. The voltages can be different, but must add up to the original voltage. We should note, though, that this is not how things are normally connected in a building system. We almost never connect things in series. There are some very special cases that we might do that with a high resistance ground, an industrial plant, and some other things like that, but we probably won't get into that in this course. So the next way we can connect our loads is in parallel, and so this is where all the inputs are tied together and all the outputs are tied together. So in this case, whatever the voltage is here, remember if we go around our loop, pick any loop, the voltage across this has to equal this voltage. So pick a different loop here, this voltage has to be the same as this voltage. So the voltages then would have to all be the same. So loads in parallel, the voltage across each load must remain the same. So this is more what we see in a building where everything is 120 volts. So we can express this mathematically as the total voltage has got to equal to the voltage across V1. It's also equal to the voltage across V2, R2, and so on and so forth. So now, though, the current through each load must equal the total current source. So we don't necessarily have equal current through each of these like we did with the in-series current. So we have the total current here, and some will go here, some will go here, some will go here. And so through R1, through R2, and out to Rn. And so this can be different. So, but the total of all of the currents through all the devices, when you add them up, has to equal the total current. So this can be expressed as I equals I1 plus I2 plus I3. This is how things are normally connected in building systems. So this is the way we'll deal with most electrical circuits moving forward in this course. So with loads in parallel then, how do we characterize these loads? So one thing we might want to know is what the total load is on the circuit, because this will be the total load that we need to give to the utility company. So when we do that, we know from electrical circuit theory that the 1 over the total resistance is equal to 1 over R1 plus 1 over R2, so on and so forth. We can do some algebraic manipulation, and we see here the total resistance is 1 over 1 plus R1 over 1 over R2, so on and so forth. So what this should hopefully demonstrate to us is that as we add loads, right, our total resistance is going to go down, and so there will be more and more current flow in the device or in the circuits. So let's talk about power. So power is generally defined as the voltage times the current. This can be expressed mathematically as V times I, and then we can take the identity from Ohm's law, substitute this in, and get a couple of different representations of this. So it's also equal to the current squared times the resistance, and also equal to the voltage squared divided by the resistance. All of these should give us the exact same results. Now when we go to three-phase, we're not going to show the reason why for this mathematically, but we will see that the power that here is also the voltage times the current, but we also have to include a multiplication factor of the square root of 3. So just as before, voltage times current times the square root of 3, and then again using the Ohm's law identity, we see that we have square root of 3 I squared R and square root of 3 times the voltage squared over the resistance. So another thing we worth mentioning here is you have potentially two different types of systems. You can have one where the current flows directly and constantly and never changes, and then you can have one where the current is alternating, which incidentally the voltage will be too. So this is called an alternating system. And so you can see in the DC voltage system, you just have a DC voltage level. It's constant, stays the same, never changes. And this is much like a battery, like a 12-volt battery or a 9-volt battery. The voltage stays the same all the time. In an AC voltage system, the voltage is constantly alternating in a sine wave pattern. And so you'll have a peak there, which is the blue circle, and then zero crossings, which is the purple circle, and it's constantly alternating. And so in the United States, this voltage current relationship alternates 60 times a second, or 60 hertz. So at the dawn of using electrical systems in buildings, there was a large debate over whether we should use DC or AC systems. Of course, Thomas Edison championed the DC approach, and then Nikola Tesla championed the AC approach, and went back and forth for a while. They built systems using each approach, but ultimately the AC approach proposed by Tesla won out, and we're going to talk about reasons for that here in just a moment. But pretty interesting little graphic here, talking about this contrast that went on for a while. So we want to talk about the concept of voltage transformers, and so this is probably the primary reasons that AC voltage systems won out, and that is that we can use a voltage transformer to vary the voltage in a system. And so this is done by utilizing the turns ratios. And so if we look here, we can have a certain number of turns on this side and a certain number of turns on this side. And so we'll have our primary voltage and our secondary voltage. If we take that ratio, it should be equal to the number of primary turns divided by the secondary turns. And so this is important in transmission because you will have voltage drop as we send current along a line. So when you have that voltage drop, if we start out with a very, very high voltage, it doesn't affect us as much when we get to the end of the transmission line. But we don't want to use the high voltage in our house, and so we can use one of these voltage transformers to step the voltage down to the voltage that we are accustomed to seeing in our home. So as an example here, we could have a transformer that has 2,000 turns on one side and 1,000 turns on the other side. And so if we put 240 volts on the primary side, once it goes through this voltage transformation, we would measure 12 volts on the secondary side. And again, this is just a function of the turns ratios. In addition to that, not only do we have voltage transformers, we can also have current transformers. And so these are derived from Maxwell's equations. And we know that as current flows through a conductor, if we were to sum up the fields around this, it'll create a current flow in an ammeter. Well, the ratio of the current flow in this cable and in our ammeter is going to be a ratio of how many turns are on this winding here. And so just like before, we can have one current here, and then we can step that up or down depending on our turns ratios here. So as an example, we see here if we have a 300 to 5, which this is a common CT used in industry today. So for every 300 amps that flows through the conductor here, we'll read a step of 5 amps on our ammeter. So the reason this is important is this is used in metering. So the power company, the meters that they use, they can direct meter up to 400 amps, but once it gets above 400 amps, they don't want to direct meter that anymore because it would take an incredibly large monitoring device to meter that much current flow. So what they do is they use CTs, or current transformers, and so they run the service conductors through here, and then it steps it down. So if you were to have a 3,000 amp service, I really only need to measure 50 amps out here, which is much more manageable. For the power company, it makes more sense. So what do these current transformers look like? Well, here's a picture of one on the top left. This is a very common one. So you'd run the conductor straight through the hole of the donut, so to speak. And then we have our leads here that we connect to, and this is what we'll have our step down, ratio down current that we can measure there. And so here's some pictures of them in actual use in the field. So you can see they're running the conductors through here, and they have the meter connections here. And many times they'll put them in a cabinet, so we call this a CT cabinet. So you might see a big cabinet right next to where the service comes in, and a meter sitting right next to it. And so what that is this, it's a metering cabinet. So they'll run the service through there, and then they'll run these smaller meter wires out through a smaller conduit to the meter base, and then they can measure how much current is used. Sometimes they even put them up on the pole, as you see here. So those are CTs there. So one thing that's worth noting is um, that can be problematic with AC power is that there can be a phase difference associated between the voltage and the current. So if you have a purely resistive load, the phase and the current alternate together at the same time, as we see here. But once we introduce any type of inductive load into our circuit, then we'll start to see the phase difference here. So what that means is they're not crossing the zero crossing at the same time, and they're not peaking at the same time. Same can be said for capacitive loads. This way it shifts it in the other direction. So this is usually called lagging. This is called leading. And so here you see that the current is lagging behind the voltage. Here you see that it appears that the current is leading the voltage. What we'll see in real life is more the middle one, the inductive circuit. And the reason for that is electric motors are primarily inductive loads. So the more and more motors we add, the more induction we're putting into our circuit. And so there's many things that utilize motors. There's HVAC systems, they have motors in them. You can have elevator motors, you can have garage door openers, you can have garbage disposals, your dishwasher, your washing machine. All these have some type of electric motor in them, so these will be putting in inductive load. In smaller applications, most of the time this phase shift is not that great compared to the resistive load in here as well. And so we usually neglect it. We just say that there is some mismatch, but we can live with it. But in larger industrial loads where they have, or applications where they have really big motors, this can become a problem. And let's look and see why that might be. So here we have a graph, and we remember power. We get power by multiplying the voltage. Here's represented with E instead of V, times the current I. So in this case, we're multiplying this curve point by point all the way around, and that gives us this green line here. So you can see that would be a graph of our power flow. Well, if we come over here where we have an inductive load, these things are not in phase with each other anymore. So you see everywhere either of them cross zero, the product is zero. And then the peaks are never together. So the peak here is much lower than the peak here. And so you can see we don't get as much power output when we are not in phase. Same thing with pure capacitive. So this is a bit of a problem, or can be a problem if it continues to grow. So the way we characterize this mathematically is we refer to a term called power factor. And so power factor is defined as the true power divided by the apparent power. So the apparent power is when we're just thinking of everything in phase, purely resistive. So that's the maximum that we could get with our voltage times our current. The true power is the line that we get when we multiply the actual current waveform times the voltage waveform, like in the second and third graphs on the previous slide. It'll always be less. So you can see once we take that ratio, we'll either get a decimal number or we can correlate that to an angle, what we call a phase angle. And so here we would say we have a power factor of 0.7, or you might hear people say 70% power factor. So the reason why this is an issue, and this is a graph people often use to talk about this, we define this total power as, again, when the current and the voltage are totally in phase. So this is the maximum we can get, right? So as we start to go out of phase with a phase shift, remember our current and voltage aren't lined up together, so we start to see what's the real power. That's that smaller green line we saw in the second and third graph before. And so this is what we pay for, though, the total power. This is what we can actually utilize. So you can, as you can imagine, as this shrinks down more and more, we're paying for a lot more power than what we're using. So in an industrial application, this can be a problem. There's ways to correct that, which we may talk about in a later lecture or later talk, but basically by adding capacitance back in. But So in this case, it's comparable to like a cappuccino, right? You pay for the entire cappuccino, but the amount that you actually drink is this coffee part, and the froth, doesn't really add any substance other than visual satisfaction, I guess. But the bulk of what you're paying for is the coffee down here. So another thing worth talking about quickly is single phase versus three phase. So in our houses, we always have single phase. So we just have one phase conductor that will alternate between the maximum and minimum. It's usually 240 volts. Or if we go in between the neutral, it's 120 volts. Well, the problem with this, or the potential issue with this is, if you're running a motor and you've got a pretty good load on the motor, you can see that there's 3 times in a cycle to where there's 0 power being delivered to the motor. All right, and then you can see between the 0 and the half mark here, half peak, and down here as well, not a whole lot of power is being delivered to the motor. It doesn't have consistent drive on it. So if you have a pretty heavy load on that motor, this can cause an issue, and it makes it difficult for the motor to maintain torque. And so this can be a really big problem in industry, when they have assembly lines going and they have different processes going, especially with loads that are under heavy load. So what they figured out was, well, instead of just running one phase conductor to our load, we'll run 3 phase conductors to our load, and we'll vary the alternating pattern of each of these by 120 degrees. So we'll put a phase shift in there ourselves between these 3 sources. So it's like we have 3 different voltage sources, and they're all out of phase with each other. Well, now you can see that at any given time, we always have at least half of the power or more being delivered to our motor from one phase or another. And so this can provide a much smoother run for the motor, especially under heavy load, and help it maintain torque while it's under load. So when we take this power factor into consideration, how does that affect our power calculation? Well, we just simply multiply that power factor times our original definition for power. So you can see here for each of the definitions, I just add a factor for the power factor itself. Remember, when it's a resistive load, the power factor is 1, so we go back to our original equation. Same thing's true for 3-phase power, whereas we had the original equations times square root of 3. Now we just add a power factor correction to our calculation here as well. So let's look at some examples. For the first example, we're going to look at 120 volt, 1 horsepower, single phase motor. So that means we'll be running 1 phase conductor to this and a neutral. So from the National Electrical Code, and we'll learn how to do this later, but for now we see that we would expect this motor to draw 16 amps under full load. So now we have our voltage and our current. Well, we recall that total power is calculated by multiplying the voltage times the current. So if we plug those values in, we'll see we'll have 120 volts times 16 amps, and that should give us 1.92 kW. So this value here is what would be entered into the panel schedule for this, and we would have a single pole breaker load, so it would just take 1 slot on our panel schedule. So this is all we need for a single phase load. So now if we go to example number 2, if we have a 208 volt, 3 horsepower single phase motor, again, from the National Electrical Code, we expect the amperage draw at full load of 18.7 amps. So this is a single phase motor, but it's given us 208 volts. So the way we do that is we run 2 phase conductors to the motor. So the total power here again is voltage times current. We enter our voltage, we enter our current, and we get 3.89 kilowatts. So being that we've run 2 phase conductors there, we have to take our power, total power, 389, and divide it by the number of phase conductors, which is 2, so we get 1.94 kW. So this is what is entered into the panel schedule for the 2-pole breaker load for each phase. So this will take up 2 phase slots on our panel. So one will have 1.94 and the other will have 1.94, which will give us our total load there. final example, we're going to look at a 480 volt, 10 horsepower, 3-phase motor. So this is different from the others. We have 3 phases, so we're running 3 phase conductors to this motor. From the NEC again, we'll talk about later how we get this, but we see that it's going to deliver, or we expect it to have 14 amps at full load. So this time, remember, we're using the square root of 3 times the voltage times the current. So if we plug those values in, 480 and 14 amps, we're going to get 11.6 kilowatts. So again, we have to think of this in terms of the total power divided by how many phase conductors we are sending to this load. So we'll take our 11.64 and divide it by 3. So that's going to be 3.88 kW. So this 3.88 kW is what is entered into our panel schedule for the 3-pole breaker load for each phase. Remember, this should take up 3 slots on our panel. So now we've looked at examples of single phase and 3-phase loads and how we calculate them and enter them into load calculations.